the organizers for bringing me here. It's a wonderful city and this is my first time in Mumbai as a whole. So I'll just start off with my thesis work. It's an application of Moonshinein symmetry in N equals 4 supersymmetric black hole theories. And the talk is based on these two papers that I wrote with Justin. First, I'll briefly start with extremely simple things. If you consider a single closed bosonic string compactified on a torus, the oscillator modes can be written like these, and the Hamiltonian can be written like these. Then k is an integer, and I basically call the alphas as the left movers and the other ones as the right movers. Then if you want to evaluate the partition function, it gives you a Dedekind eta function once you complexify this temperature here. Similar traces you can actually evaluate for the fermions also, and most of my work is actually based on these kind of computations of traces. Can everyone hear? Modular functions, I will define them with a rough definition. We basically can be defined, it's a holomorphic function in the upper half plane, and it can be written like these, and k can be an integer or half integer, and the zeta is a phase, and if zeta is 1 and k is greater than 0, and it's a fz is then fz we call as a modular form.
So what do you mean by zeta is a phase? Because all these things are complex, right? ABCD are complex?
Yes, yes,
So
but
ABCD
actually
is not complex, but
no, ABCDs are integers on
zeta
SL2Z.
depends on the z and this thing also.
Zeta depends, I mean, say, do I have a chalk or yeah, suppose you have a Dedekind eta function, then if I do if I just make tau 1 to tau plus 1, I have a to the power I pi by 12 eta of tau.
Yeah.
So I'll call modular functions to be those which can involve this kind of phases.
No, but wait, if you do -1 over tau?
Then I don't have. Then it's what? Then also I have actually. Sorry, it's this. There is a square root of minus I in this. So for these kind of functions, I'll also call as modular functions.
What I was asking is a simple question. The zeta could be a priori a function of tau, right?
No, no, no. Zeta is actually a phase. I mean, not a function of tau, but a function of ABCD.
So it never involves?
No. This zeta, this tau now, I have written it as z. That part is only here. That comes in only in the weight. And if fz is 0 at the infinity, then it's a cast form. These are some examples of modular functions and modular forms. And this is the first cast form. And inverse of 1 by zeta to the 24 comes for 24 bosonic 24 bosons compactified on a torus. We frequently encounter this gamma naught n group, which is a subgroup of the SL2Z, and we have a weight 2 modular form in these subgroups, which is given in terms of the Eisenstein series of weight 2, which is not exactly a modular form, but a quasi-modular form. There is basically this is the statement, but when I introduce mock modular forms here, and even though I'll actually talk about these at the end, but it's easier to introduce them here. We actually don't have any weight 2 modular form in SL2Z, but there is a mock modular form. This is E2, and this function E2, if you subtract out minus 3 by pi tau 2, then it transforms similarly as these. And this minus 3 by pi tau 2 will be called the Eichler integral, and this E2 hat is called the completion of E2 or the completion of the mock modular form. And every mock modular form h tau is associated with a similar function g tau called the shadow, where this shadow and the Eichler integral are related like these. And for E2, this is a very simple shadow, it's minus 12.
So what is the definition of mock modular form?
This is actually the definition of mock modular form. If you have a mock modular form, there will be associated function, which is a shadow function, and the shadow will be related like this. And once you complete the function h plus g hat, that will transform, that will have the modular
So the
property.
last statement makes sense. The H hat
H hat
nicely.
will transform nicely.
Right, and that's not holomorphic because there is an
Yes,
anti-holomorphic
yes.
piece also.
Yeah.
And
There will be
there is
an
a unique way to separate that into a holomorphic and a non-holomorphic thing, for which the holomorphic piece is called modular. Is that what you're saying?
Well, it's a differential equation. It might not be completely unique though. But in this case, I'm not sure about the uniqueness part.
Okay. So H hat is a more natural object, right?
H hat is the more natural object which transforms correctly. But we'll extract out the H in our work.
So what's the star and what's the bar? Yeah, sir.
Oh, sorry. G star is basically not the bar. It's actually this. The cycler integral. It's an object.
Star is part of the notation.
Star is part of the notation.
And
Sorry.
what is G of tau?
G of tau is the shadow. Here is minus 12 in the E2 case.
Oh, I see. Okay. Oh, I see. So this G star cannot be arbitrary function. It has to be of
No,
star.
yes.
And then perhaps maybe it's unique also.
That I don't know. I'll not comment on the uniqueness of this.
Now G on the right hand side is the H.
Uh,
What's that G?
that G is the shadow actually.
That's also tau comma tau bar actually.
No, that G.
There is.
Well, that G might have a. Here actually G is minus 12. Here G is not a.
Right hand side G is minus 12.
Right hand side
What's
G
the
for
G
this
star?
case is minus 12. Yes.
So this G star is the non-holomorphic piece, but it cannot be arbitrary.
Huh,
Has to be
because
related
it
to the
related with this
piece.
holomorphic piece.
Oh, the holomorphic piece
G
was
of
H,
tau.
I thought. No. So G of tau is a holomorphic thing from which you construct this non-holomorphic thing, and the G star can have only that form.
Yeah.
So
We.
not any arbitrary
Yeah.
function. Okay.
Okay. Shall I proceed? So basically, the first example of Moonshinein was seen in this form, which was called the J function, and if you Fourier expand this J function, then these initial coefficients of q, q square, and q cube could be written in terms of the dimension of irreps of the monster group, which is a huge group of 10 to the power 53 order. And this was the first example where we saw. Now, I will just briefly describe the Jacobi forms also. These have two properties. One is similar to the modular function properties, is called modular property, and the second property is called the elliptic property on the torus. And this m is the index of the Jacobi form and k is the weight. Now, if you consider the elliptic genus of K3, it is a trace over the Raymond sector.
Sorry, can you flash the previous slide?
Sure. This trace is over the Raymond sector. And if you Fourier expand these in terms of this q and well, you can call it y or something in terms of the integers m and l, then elliptic genus can be seen to be holomorphic in tau and z, because the right movers will preserve the supersymmetry and only count the ground states of the fermions. If you evaluate the trace over a K3 manifold, the result becomes 8 times these theta functions, and these theta functions, the combination of these theta functions form the Jacobi form of index 1 and weight 0. And there are some few simple models of K3 where you can explicitly do this computation in CFT computations, and the Hodge diamond of K3 can be read off from them. And most of the times in our work we have used T4 by Zn, but there are some orbifolds cannot be done like that, I guess. We can have quotients on K3, which is where we can compute a similar object like the elliptic genus. It will be called the twisted elliptic genus, and that will cut off the H11 of the Hodge numbers. Now, if n is a prime, then these are the this is the way that the H11 reduces, and for up to 7 this thing is actually done, and we will call this Zn action by some G prime. Now, if G prime is the yeah.
So K, you had another column in this.
K is basically just H11 was written as 2K.
Oh, sorry.
H11.
K is this weight, right?
K is this weight. K is this weight. But this formula actually holds only from prime n. Otherwise, H11 can be still read off. I mean, there is a way to read the K.
And how about the index in these cases? They are the same.
Uh,
The weight and the index, right?
This is just a number. This is just the Horn's number. Twisted elliptic genus. I haven't, I mean, actually defined it yet. This
Not
is
twisted, but just normal elliptic genus.
normal elliptic genus is a weight 0 and index 1 object.
For K3.
For K3. Actually, for torus it's 0. Yeah, right. For K3. So, if you have a G prime action of this quotient, then you can do the quotienting of this K3 in terms of this G prime action, and you can still write the twisted elliptic genus in a Fourier expansion way. And for this for up to Z, this result was actually done by Ashok, Justin, and Dilip Chattopadhyaya. For n equals 2 orbifold of K3, F00, F01, F11, F10 can be computed in terms of these Jacobi theta functions, and these can also be related to weight 0, index 1 and objects of I think normally for K3 this twisted elliptic genus FRS can always be written in this form, at least for the cases that we have studied, is some alpha times A and beta times B, where B is actually a weight weight minus 1 object, and this beta will have a weight 2, and it is a weight 2 form of gamma naught n or something normally.
So can you just flash the definition of the twisted index?
Oh, this one. It's actually you twist it with a G to the R and you insert a G to the S, R and S.
And the modular, by that you have some exchange of RS also?
You can, yeah, from one goes, yeah, the transformation property, it's a little later, I'll go through it.
Say all these things that this is index 1 and so on.
The transformation property works in that way. If R and S, if you interchange, then S, if it becomes S and R, how it's related to R and S, that's there. I mean,
yeah, that's what you mean by this is new definition, right?
Yeah, it's a new definition. Yes.
And also these are modular forms under the congruence.
These are modular forms.
As such, when you write them, then you will also probably give the action of the generators which are not in gamma 0. That's how you have split it.
I don't understand.
I mean, we have gamma 0 n.
Yes.
When you write these as modular forms, are they just modular forms under gamma 0 n?
These are modular forms. They can be transformed under gamma 0 n. Yes.
So S is usually not part.
S is not a gamma 0 object, but there is actually a direct way of writing the FRSs, how it transforms to different
So that's an
objects.
additional thing that we can.
Yeah, that's actually an addition. But that also comes from gamma naught n only. These objects of gamma naught n, they have this 3K involution also. So using them, you can go from one to the other. So anyway, the first relation of this Moonshinein was seen by this Eguchi, Oguri and these people. So they could write the elliptic genus of K3 in terms of the short and long representations of n equals 4 superconformal algebra, and this AN1 in this AN1A is actually the trace of the dimension of ellipse of the M24, Mathieu group M24. M24 is actually a subgroup of this big monster group that we had. Then the first few index of this A1A are these, and this 90 can be written as 45 plus 45 bar, and this 462 can be written as 261 plus 231 plus 231 bar, and this similarly.
How about the first
24, 2.
previous slide?
Oh, no, not this and not the 0. It starts from n equals 1. Actually, for the j function also, when you see, it's actually starting from q to the power 1 only, where they found the relation between the coefficients and the monster group readers. Now, one can write this a n like this, and from the character table you can just read it. Now, similarly for 2a orbifold, this is the formula, and say a and 2a can also be read off from the character table, and for a general G prime orbifold you can write it still with the superconformal characters, and this chi is actually the Witten index and it is given by 24 by n. Now, for the first few values of a and 2a I have also actually given here. It was checked by Eguchi, Cheng and these people, Gabardiel, and these coefficients can also be read off from the character table of M24. There are 26 conjugacy classes of M24. I have listed these classes over here. There is a type, this is the first slide, which is actually, these classes belong to M23 itself. M23 is when you keep one of the objects fixed, and probably how many of them are, some 15 or 16 of them, and the rest you cannot actually fix one of them, all the objects move, and so the cycle shapes are like that. And using the cycle shapes and all, we can predict how the twisted elliptic genus would behave.
Is there a definition of M24 that is easy to say?
M24 definition?
Or M23, what does it mean? Because you mentioned
no,
that
I
one
can.
of the object is kept fixed.
Yeah, M24 is a subgroup of S24 only.
Okay. But
So, in S24 itself, if you keep one of the objects fixed, then also you will get a subgroup. M24 is similar to that only, but it's very difficult to say, describe the group. It's a huge definition actually. So, and it's not like not a cyclic group like SS. So, might be something similar to the alternating type. I'm not that sure. But and we have mostly studied these two and the rest of the M23. Now, using the Mackay-Thompson series, which is associated to these 26 conjugacy classes, one can write the F01 for these objects, for these twisted elliptic genuses, and closed form expressions for these were found by these people, Eguchi, Cheng and Gabardiel, and in fact, for the order 4 object, even Suresh had written some papers before. So, and these M24 symmetry of the elliptic genus actually kind of points to existence of 26 quotients of K3, but construction of those are not yet, as far as I know, are not known that well. Modular function, and here you have the property of the FRSs when they transform. Modular transformations from FRS from one sector to the other can be related in terms of these A, B, C and Ds. But here also you can see, if you have an order 4 object and you are in a sector something like 2, 0 or something, then whatever ABCD you give in the right side, you cannot reach something which is even and odd or both odds. You cannot reach something like 1, 2 or 1, 1, something like that. So, some of these are become some subset among themselves, these are things are called orbits actually, and we have to determine all the FRSs in case we want to proceed towards finding the dion degeneracies. And these expressions are actually all mod n, and the ABCD are SL2Z elements again. Now, explicit closed form expressions for all the components of the FRSs were obtained by us for the type 1 that I showed, and first 2 cases in the M24. And to determine the twisted elliptic genus in these sectors, we which are not related to F01, we had to use I mean, we had to use the cycle shape of the objects and predict how it would behave. And for 2b and 3b, which were the other two, which were of this order, I mean, which were actually of order 4 and 9, we could not use the cycle shape, but there is a model called torus model. When if you sum over all the twisted elliptic genus, it becomes 0. It's something called quantum symmetry, I guess. And I mean, for the 2b, actually there is a explicit construction of the F01 by CFT. It was done by Gabardiel in 2013. Now, using the twisted elliptic genus, we can compute the Hodge numbers and identify the 4b, 6a, 8a and these 2 to 7 primes to that of the CHL orbifolds. Here we have a description of the, I mean, here we have a list of all the FRSs, and you can see it's kind of involved with the expressions and all. And to reach the twisted sectors, we needed several identities like this E8 tau plus half, how it would be related to E2 Z4s and all, and tau would be replaced by some minus 1 by 2 tau and minus 1 by 4 tau and something like that. And one thing I have to emphasize is after beyond 8, order 8, all the objects that we found were non-geometric quotients of K3, but here the even Kähler form, the H11 becomes 0 or negative, so the Kähler form also gets projected out. And for 11 itself, for 11A conjugacy class, which is an order 11 object, it vanishes. And there is an explicit, but still there is an explicit CFT construction with 6 SU2 level 1 theories, whose twisted elliptic genus F01 is given by the 2b orbifold, which I was talking about. It was done by Gabardiel. Now, let us move on to how we utilize, I mean, how we use this twisted elliptic genus to determine the black hole degeneracies. Now, if you consider the type 2 theory on K3 times T2 orbifolded with an order n object, where this Zn action is a G prime action on K3, which is similar to the M23 and M23 and M24, and a shift of 1 by n on one of the T2 circles, which preserves the supersymmetry. And these compactifications preserve n equals 4 suci in d equals 4, and it gives you a class of new string vacuum. And each of these solutions would admit 1/4 BPS states with both magnetic charges and electric charges. And for large charges, these could be identified in with supersymmetric black holes. Now, the generating function for the degeneracy in genetic function for finding the degeneracy of dyons in these theories is given by this minus B6 object, which can be written in terms of a modular form, which is not exactly of a modular form of SL2Z, but of SP2Z, this phi hat, or some subgroup of that, phi tilde. And in this integral is done on a contour in the complex 3 plane with large imaginary values of this rho, sigma and V. And it was first done by this Dijkgraaf, Verlinde, then Ashok and Justin, and Dilip, they extended this, and Davolkar had also extended the methods and all. This is the definition of the contour. And this phi hat is actually called a Siegel modular form associated with the twisted elliptic genus, and it can be given by these, these CBRSs are actually the twisted elliptic genus components. The Fourier coefficients of the twisted elliptic genuses can be written in this CRSs. I have given the B, but it's for these cases it's not exactly necessary that much.
Why is it combined in this way to construct this phi tilde?
Actually, this is a partition function, and the counting has been done by Davolkar and Ashok, these people, and initially it was done by
partition
Sorry?
Phi tilde is the partition function.
Phi tilde is a partition function. 1 by phi tilde is a partition function. With this electric magnetic, I mean, they have both electric and magnetic charges. This Q and P's are electric and magnetic charges. And you write the partition function with this form, with this phi.
So
And
it's a partition function as opposed to the elliptic genuses.
no, it's not a partition function of the elliptic genuses.
No, as opposed to the elliptic.
Yeah.
So there is no minus 1 to the f. Is that the difference?
Let's look at let's understand what is this B6 elliptic vector.
Minus B6 is actually, it's actually the, I mean the fermions, I mean when you break the supersymmetry, these are 1/4 BPS dyons. There will be, I mean there are basically 12 supersymmetries which are broken here, and it can compute the 6 helicity trace which can be written like these, and this 2h, h is actually 1/4. So this B6 actually becomes an integer, and it's actually a trace, and the trace is over all the set of charges, all the fermions carrying the same set of charges.
Why does one want to compute this 6th helicity trace?
Yes, where this come from? This definition?
Okay.
I think that's the
Sorry.
first index which is non-zero for these.
Oh yes, for before it becomes 0 for these cases actually, yeah.
But the elliptic genus doesn't have this. Elliptic genus is just the trace minus 1.
Hmm.
So that is the result.
No, this is in wait, the elliptic genus was for the word sheet here.
Okay.
This is just this twisted history index for the space time string here on K3 times T2. So if 4 and supersymmetries are broken, then B2n is the index, which is first
And
non-zero.
that is the one that is related to the word sheet elliptic genus.
Yeah, in a very convoluted way.
Yeah, that I don't, I mean that honestly I don't know.
In fact, that 1 over phi tilde, at least in the case of just heterotic on T6, was computed by
Diagraph, I
diagram
don't know.
validated as the genus 2 partition function.
Yeah.
Just like 1 over eta to the 24 is the genus 1 partition function, bosonic strings. This was a bit more complicated.
Sorry. Anyway, so you can read this B tilde and alpha tilde is 1 and beta tilde for M23 objects is 1 by n, and normally n is the order of the orbifold action, and these are weight k objects in appropriate subgroups of the sp2z. Modular property for these objects can be written in this form. This omega is a 2 cross 2 matrix and ABCDs are all 2 cross 2 matrices, and they have this sp2z property or some subgroup of it. And k is related to the, I mean to the low line coefficients of the elliptic genus of K3 or some twisted elliptic genus. Now let us move on to the test for these degeneracy formula. The first thing is that this minus B6 should be integers, and that certainly is as long as your CRSS are integers. So if your twisted elliptic genus, not CRSS, but this expression, the CRSS with this phase, this Fourier transform of this FRSS are integers. So then you have it guaranteed to be integral. But we also need to check that this minus B6 is positive, minus B6 is needs to be actually positive, and that is very complicated because the expression is like there is a minus 1 to the power q dot p dependence is there here. So that also we checked for non-trivial objects, and we did find some violations, we did find some matching, most of them were matching though. Now for the phi 10 is basically when you have just a K3, there is no orbifold on it. This I mean The sufficient condition which Ashok gave was this q dot p should be greater than 0 and the area of the black hole, the classical area, should be greater than 0, and and q square and p square should also be greater than 0 individually. Then this minus b6, evaluated from the Fourier expansion of the Siegel modular form should be positive, and we did see some, I mean, not for phi 10, but for certain objects we did see some violations to that. For K3 case, for low lying magnetic charges p squared equals 2 and 4, this conjecture was proved by Brinkman and Murthy, and for the orbifolds of 2, 3, 5 and 7, Ashok verified it for low lying coefficients that minus b6 did turn out to be positive. We constructed the twisted elliptic genuses in all the sectors, and we basically need all the sectors also. From F01 only you cannot write the you cannot write the minus b6, and corresponding to all the conjugacy classes of type 1 and 2 types 2 in type 2, and here all the results were actually minus b6 did turn out to be positive. And I have a list of the results which are positive, and if q dot p is 0 or greater, then we did see all positive results, even for non-geometric cases. Here this one is actually a non-geometric object. Now let us move on to degeneracy and the saddle point computation of this integral, and there is a constant relating to two of the Siegel modular forms with different, I mean they are under some subgroups of sp2z, but those are different subgroups. And when we want to do this integral of minus b6 using a saddle point method, then there is a Fourier transform of this phi tilde to phi hat, and these are the variables of this rho tilde and v's are I mean can be related in terms to the previous phi tildes in this way. And here we have actually a constant C1. This constant was never I mean explicitly worked out before.
Yes. You computed the twisted elliptic genus with R and S
Yes.
group elements inserted. So when you compute B6, where does that enter?
It enters through this. This C is actually having the R and S index.
And
These are the Fourier coefficients of the FR.
is to be summed over.
That is to be summed over, actually product over, no? Because the R should be product over and summed over this with the phase. Summing is with the phase actually.
So you fix an R and then you
Yeah.
do that
Discrete Fourier transform and
get that exponent.
yeah.
Then you take product over.
I missed with this R and S is orbifolding by some discrete symmetry.
Yes. R is the twist and G and S is the insertion of that. R and S is of the some element G to the R and G to the S.
And in space-time you are looking at K3 modded out by that discrete symmetry?
Yes. Modded out by that at times this is a times a 1 by n shift on the T2. This is a type 2 theory.
So basically you've got a moduli space of K3s and somewhere in that moduli space you get these orbifolds.
Yeah,
right?
for K3 wait. Shall I move?
Sorry, these discrete symmetries exist everywhere in the K3 moduli space or only at special locales?
I don't know, I am not fully confident, but at certain orbifold limits you can compute it. So when we do this Fourier transform, we have to do, when we want to do it with the saddle point analysis, we need to make a modular transformation of this kind, and there is a constant related C1 which is 1 for K3, and this constant is very important, otherwise at low lying degeneracies this I mean the saddle point will be quite off from the actual degeneracy which we compute. So, phi hat can be phi hat at v tends to 0 limit can be broken down to an eta product, and this H is some k plus 2 weight eta products of, I have a list of this H sometime. Sorry? There are 3 objects, q squared, p squared and q dot p. These are the moduli, I mean which comes with each of them. Which kind? Yeah. Okay. Sorry, where is phi hat? Here. J.
But what is it?
I mean phi and yeah, it of course is chemical. Now for the using saddle point analysis, taking the leading saddle, this is the expression for the entropy, and there is a log of ln nc1 that that is not exactly known yet how to find from the gravity side, and this C1 can be written for an orbifold which is of this M23 conjugacy class related. The C1 can be written like this n to the power k plus 2 by 2. Now this k
Where did that C1 come from? How did one
from the
compute that?
transformation of this phi tilde to phi hat.
So we know the expression for phi tilde. Under this transformation, we can read off the value of C1. Is that how it goes?
Well, it's actually, I mean phi tilde and phi hats are given by 2 complicated integrals. These integrals can be done using unfolding technique. So, both of them are done that way, and then then you have to read off, and I think the phase also depends on, the C1 might contain a phase, but phase is taken to be real such that the whole thing becomes positive ultimately, since you are reading off from 1 by phi hat or 1 by phi tilde, this minus b6 should be positive. So, yeah, so basically you get it as a mod squared and you can read it, but also but that's also important. That's the main method actually, and we computed that in our paper, but I don't want to go into that.
But C1 was computed earlier.
No, see, there is a constant, this was known,
Right.
but the C1 was never, C1 was never computed before. And C1 is actually very important, that we will see here in the next. The weights the K are like these, and I won't go into details, and these are the eta products for the H that we have written. Now the saddles, if you compare the statistical entropy of the leading saddle and the asymptotic one, the S stat is the S stat is the when you compute it just from the minus B6, and S1 is with the leading saddle, then the difference is actually quite low, this delta difference. But if you don't take the C1, then the difference is actually, the relative percentage is actually something like around 30% on an average. And this for the orbifold 2A, which is in order 2 action, and this minus ln C1 if you don't include, these are the results. So, and also in the subleading saddles, we also computed the subleading saddle in the 2A case, and the first for the without any orbifolding, this was done by Ashok and Namamita, and we computed it for the 2A orbifold, and the constant was 16, and without the constant, with the constant you actually have this is the degeneracy, not the S actually, not the entropy, but the constant is relevant because for one entry I actually computed that if you ignore the C1, it becomes 316, and which is about 14% of the actual degeneracy. So, the contribution will be huge if you do not take the C1 value, and this is the same C1 which goes to all the different saddles, all the subleading saddles.
Sorry, C1 is like a logarithm, it's what?
Log of n time, sorry, C1 is n to the power k plus 2 by 2 normally, and log of C1 is actually 16 in this case, yeah, right. But you normally have ln n C1.
And C1 from space-time point of view comes from what?
We do not know.
Okay.
That is something which actually do not know. At least from the gravity side, there is no knowledge on that.
C1 is some correction about a given saddle point.
No. C1 is the same number for all saddles, but it is for the it actually comes like if you have an eta function, if you had something like eta to the 1 by eta to the 24 tau as your partition function, which is there, which was done by Davolkar at some point, then to do this S1, to compute the leading saddle, you have to do this eta to the minus 1 by tau. So, there is a similar transformation of phi's also, like phi, the phi is in sp2z form. So, rho sigma and v goes to phi hat of rho tilde, sigma tilde and v tilde, then it goes to something like this phi hat, and these rho sigmas and v's are related to each other with a modular transformation. And if you do that, then actually it becomes this phi hat rho sigma and v is some C1 times some weight times phi tilde. So, this is the C1, and it comes
C1 times this phi tilde.
C1 times phi tilde with some weight might be there.
And then phi tilde that is expanded in saddle points.
Phi hat is actually expanded in the saddle points.
Phi hat is expanded in saddle points. So, I just want to understand C1 from the point of view of any given saddle point. Is it a multiplicative constant outside?
It's just a multiplicative constant.
So, it sounds like one loop, right?
Yeah.
It sounds like a one loop correction.
One loop. Yeah.
The universal one loop correction.
Yeah.
For example, it appears on the gravity side, it can appear in the Gauss-Bonnet.
It actually comes as a constant times the Gauss-Bonnet, so string amplitudes doesn't. Huh?
It appears just classic. It's not from doing the path integral.
Well, actually, in the path integral, we don't know how to compute it. Basically, let's just move on. We can actually this S1 that we have written. The first term is basically the Hawking-Bekenstein. The second term, this green one, is actually from the Gauss-Bonnet term. Gauss-Bonnet term which contains the moduli. But there is a constant here, and that also should be coming from the constant times the Gauss-Bonnet, but that becomes a total derivative in 4D. So, that term you cannot fix in terms of the
The tau is the axiom dilettante, so
Yeah.
it's probably not. It has all non-perturbative. I see.
that's basically this. The tau, this we can write this phi as A and S as the axiom and dilettante, and this is the Gauss-Bonnet, and there is a constant, but this you cannot fix using the
But the constant piece does not have any contribution from the dilettante.
yeah.
That sounds like one.
Yeah.
That constant should be.
Yeah.
If we could do it from the 10 dimensions, then probably we could find the origin of the constant exactly, but that we haven't tried actually. Recently this Davolkar guys, they have started this localization method, and they were they were evaluating the entropy of black holes using this localization techniques, and so far they only, as far we know, only were constructing this K3 times T2, but the orbifolds, as far I know, is their plan also. But till now, as we have seen, the C1 contributes quite a lot, some 14% even in the second loop, and about 50% in the first, sorry, not second loop, for the subleading saddle, and about 50% in the first saddle. So the C1 has a huge contribution, especially at low charges. And since there, at least the claim is that localization technique would be exact in all orders of charges. So they should be able to reproduce the C1, but till now, as far we know, that they haven't been able to find that C1. But C1, in fact, the fact that C1 is 1 is also not, I mean, not known geometrically from the gravity side. So violations of the positivity conjecture. Let's move on to this one. First, we computed this minus B6 by two proposed orbifolds of K3, which were of order 2 and 3.
I'm sorry, so
Sorry.
the positivity conjecture, this is the same as just that the
Minus B6 should be positive.
and it should be positive because it's counting states of a black hole.
It counting states of a black hole. Yeah, I mean, yeah,
This is this Ashok.
yeah, Ashok's.
Degree scale.
Ashok's.
The index is equal to
Yes. And this Packet, Volpato and Zimmet in 2017, they proposed a few models of few orbifolds of K3 which were of order 2 and 3, and at some of the low charges we found violations to that, but there was no geometric description of those models, and so we cannot always say that whether that has a string theory description. But there is T6 on type 2, which has some Z2 and Z3 orbifolds, which were studied by Ashok, Dilip and Justin at some point, and there the minus B6 was computed, and there is a heterotic description of the theory also. So we found violations to these models also at low magnetic charges. And for Z2 orbifold, I will describe the orbifold, just let me just flash the numbers and then I will just move on to the description. So for Z2 orbifold of T6, this at p squared equals 2, p squared is the magnetic charge, we observed violation of the conjecture even if the electric charge was infinite. Here is a list of the violations. The bold ones are actually the violations, but we are finding something like an alternating series, and this is for Z3. And let's move on to the orbifolds of T6.
Yeah, and what is your, you have an interpretation of this violation?
Well, it should be some hair modes, but we don't know how it comes. So, sorry. So for the n equals 4 theories, this Z2 action is for the T6 is actually a reflection on 4 coordinates and 1 by n shift on 1 coordinate, 1 by 2 shift here. And for Z3, it is for 4 coordinates, 2 of them gets a plus phase and 2 of them gets a negative phase, and the one of the circles has a shift of 1/3. And if you want to compute the phi tilde in these cases, here phi tilde can be given in this form, and again from the twisted elliptic genus you can read off the CBRSS, and there is no sigma by n though in this method because it is a torus model. For Z2 we have the F00 is 0, and these are the values of in terms of A's and B's, the A is a weight 0 and index 1 Jacobi form, B is a weight -1 and weight -2 and index 1 Jacobi form, and this curly E2 is the holomorphic part of the sorry, not curly, it is actually a gamma naught n weight 2 object written in terms of Eisenstein series. We can expand the 1 by phi 2 or any 1 by phi k actually in terms of a Jacobi form, and in terms of Jacobi forms while expanding in terms of the magnetic charges. At p squared equals 2, this psi 1 component, which is at m equals 1, this number comes. This psi 1 can be written as a product form like this, and if you just look closely to this product form, all the even powers come with a positive sign and all the odd powers must come with a negative sign, even powers of q, and q infinity squared is given in this form. Is basically the Euler phi function with the 2 tau, and so sign of odd and even powers of q actually becomes independent of z, the power of z actually, but this power of z is related to actually related to this thing, this q dot p. Z is the chemical potential with respect to this q dot p. Then there is a minus 1 to the power q dot p plus 1 in the definition of minus B6. So so it's kind of evident that you are going to have a alternating series for these cases. And this line actually, even if the electric charge becomes infinite, it will still be an alternating series only. Now, in terms of Jacobi form, the rest of these can be, we have written here up to psi 1, psi 0 and psi 1 can be written in terms of the twisted elliptic genus and hence in terms of the Jacobi forms. And we can actually write this psi 1 in terms of with two parts. One is a pole part and another part which doesn't contain any pole. So so once you are at if you no pole means pole in this z plane, so then you can just you can write this psi as a finite and the polar part. So for the Siegel modular form for K3, this subtraction of the polar part and extracting the finite part was done by this Davolkar, Murthy and Zagier, and the finite part we will see that will always contain the degeneracy of the black hole. So this minus B6 can be read off just from the finite part, and we extended this method for all the M23 cases and also for these torus orbifolds. From this DMC paper, you can write this a squared by b as this is the Appel-Lurch sum, and then there is a finite part, and this curly h is actually a mock modular form given in terms of the Hurwitz Kronecker class numbers, and this is the definition of Hn or the series expansion of Hn that you can see. And this h is actually the same function which comes for the original K3, but we have a h of n tau or h of 2 tau in this case, and h is mock Jacobi associated with these class numbers, and it can be shown, we can easily show that this h n tau will be a Jacobi form, mock Jacobi form of gamma naught n of SL2Z. So in terms of Jacobi forms for
I missed what are you trying to do now?
Oh, I am trying to write this I am basically trying to do this. I am trying to Fourier expand this 1 by phi with the magnetic charge, and I am trying to evaluate what this psi m is. This psi m will be seen to, psi m is actually a Jacobi form that can be written, basically you can just write it in terms of the FRSs. So FRSs are the twisted elliptic genuses. So they can be written in terms of the some kind of Jacobi forms only.
And what is the physical interpretation of the psi m's?
Psi m's totally don't have a physical interpretation, but if you subtract the pole of the psi m, you are left out with a finite part, and that finite part will contain the degeneracies of the black holes. When once you Fourier expand that, you can just extract the you can just extract out the minus B6 from them.
So you are trying to compute entropy of black holes on T6 mod Z2.
Or K3 or K3 times T2 mod Z, Zn.
Oh, I see.
I started with T6 because here we found the violations, and also I needed that expression that where it was totally negative. Now, this polar part can be written this way of subtracting the pole is called Appel-Lurch sum, and it has some certain kinds of properties which are like so that if it's on the torus, how it should behave and all. And the finite part would contain a Mock-Jacobi form, and we extended it to all the cases which we studied. Now, for T6 by Z2, this is psi 1, and the psi 1 p is the polar part, and psi 1 f is the finite part, and we have the results here. And here we have this h. I mean, this curly h is actually the Hurwitz-Kronecker generating function. And for orbifolds of K3, for some order n orbifold, and if G prime corresponds to M23, then the only meromorphic Jacobi form which comes are actually these I mean the same ones which come for the K3 case, and except for for the E2s and all, except for these 2 taus. I mean instead I mean for K3 actually you have just tau and z.
You know, I can't speak for the rest of the audience, but you're totally losing me.
Sorry?
You're completely losing me.
Okay.
I don't know what E2 is, I don't know what A is.
Okay, sorry,
Should I
because you
care?
were not, no actually, yeah, you should care because those are some, I mean, you need them if you want to find the result, but E4 is actually Eisenstein series of weight 4. E2 is,
you know, those words mean nothing to me.
okay.
So if there's something I need to know about them, you should tell me, otherwise we'll move on.
We found violations, that's the only thing which I guess you need to know.
Okay.
So, yeah, we can let's move on to the K3 results, and these are basically flashing some results. I don't think that I need to go to details for any of these. I think you have heard the most important part of it already. I can just go to the
make no sense to me. I see
no, sorry, because actually no, I
You
defined
probably
those things.
did it.
I actually defined each of those things. If you want, I can go through it. It's just some Jacobi forms, and it's just some Eisenstein series. That's all. Okay, so I can just summarize the results now. The leading term for the asymptotic formula for the entropy comes from the Hawking-Bekenstein for the corresponding black hole. The modular dependent subleading term gives the contribution of entropy from the Gauss-Bonnet in the effective action, and for the minus LNC1 that predicts a constant in the coefficient of Gauss-Bonnet, we are not yet able to fix it from the bulk side. The Fourier coefficients of the Siegel modular forms associated with the twisted elliptic genus of K3 have the correct sign as predicted from black hole physics by Sen, but for those which does not have this kind of those which are not belonging to this M24's symmetry or are not on K3, there we have actually seen some violations.
Say you have some.
I have a K3.
Yes.
I can mod out the K3 with some automorphisms.
Good.
I can. So these automorphisms are related to the to this this Mathieu group M23, and that Mathieu group actually shows up in the twisted elliptic genus of K3 in terms of their characters.
Let me understand these automorphisms. Are these automorphisms symmetries of K3 at a generic point in compactification?
Oh, okay. At special points we can construct it. At generic points I cannot say.
But do they exist at generic points? Or
They should be, that's the statement. For M23 they should exist at generic points. This was a work by Kondo around 1988.
So there is an M23 symmetry of a generic K3?
Of a generic K3.
I see.
I mean,
That
it's
sounds like a very strong statement. That's a big group, right?
That's actually a huge group, yeah. Some kind of symmetry is there, but that's manifested in terms of the twisted elliptic genus.
But you know, there are two possibilities. One of which is that you see a symmetry only somewhere, and then the index has that symmetry everywhere because the index
Yeah,
doesn't
yeah,
change.
yeah.
The second possibility is that that symmetry is the symmetry of the
No,
K3
no,
always.
no.
You're not saying the
No,
second
I don't think so. I don't think so. I think that it is only at. I mean, there should be K3s. I mean, there should be some moduli of modular points of K3s where
there is
this thing. Yeah,
Fine.
it's an existential proof. Okay.
So it's a symmetry of the index, but not of the K3 sigma models.
I'm not sure. I don't think so. Okay. For a generic generic point in the K3, it might not work.
Fine. So you've got this symmetry of the index, you mod out by it, and then now you were saying sometimes something.
No, I mean we
works.
can actually do the modding out in the K3. No, there is a symmetry of the K3 also. But the K3 might be. I mean, you can say you have an orbifold limit of K3 where you can construct this.
No,
but
are you saying that there is this M23 symmetry at a generic point of the K3 compactification space? I don't think you want to say that, right? That's too strong a statement.
That I think is a too strong
statement, right? So, fine. So it's a symmetry of the index.
Yeah, let's use it as a symmetry of the index.
Fine. Now you're saying that some indices are consistent with your positivity property and some are not.
Some are not.
And can you say more? Say once again which are consistent and which are not?
Yeah, when you have, I mean, for the K3, if the symmetries of the K3, they are, I mean, they are related to this Moonshinein group M24. Then there is actually this. I mean, it works. It's a correct statement.
Okay.
But if it's on T6, like we showed for this Z2 and Z3 of the T6, there are violations, and also there were violations for some K3 orbifolds which were not related to this Moonshinein. I mean, there was a construction paper by this Paquet, Volpato and Zimeth in 2017, and there they proposed some orbifolds of K3. That we don't know, but that I don't know whether it has any string meaning or not.
Okay.
But these T6 by Z2 and Z3, they have string theoretic meaning also.
Okay.
So, yeah. So basically, as there are violations and up to magnetic charge p squared equals 2, we can write the Siegel modular forms in terms of mock modular forms and Appellers sum, and for any orbifold of K3 that we studied, and we expect that this method should hold for higher charges also, but we haven't explicitly checked. Okay. Thank you. Oh.
I'm going to ask some questions even
Sure.
though it's out of total ignorance.
No, sure. Go ahead.
So the central result is the violation of this positivity conjecture. Is this right?
This one and the importance of a constant that comes from this. I mean,
C1.
C1s. Yeah.
Okay. I see. And you feel that the violation of the positivity conjecture may mean that
Hair modes. We are
hair
missing
modes
out.
of the black holes.
Hair modes out of black holes.
Could it also mean that there are other non-black hole type solutions?
Do I have to make this statement?
Do you have to make the statement that there might? I'm sorry.
Do I have to answer this? Okay, see, listen. I mean, sorry. When we actually showed this results to Ashok also, and he was of the impression that it should come from some kind of hair modes, but we have not been able to fix some hair modes. But if that's not the case, if we can rule out hair modes, then I think that's the only thing left out will be the non-black hole type solutions.
Yeah, would not be too crazy, right? You could imagine some solitonic solutions or something like that. I mean,
Maybe I don't know. I'm not sure.
okay.
I'm not the right person to answer this question.
Okay. And you also have this thing that orbifolds that belong to this M23 or whatever, this monster group, obeyed the conjecture.
Obeyed the conjecture even if they were non-geometric objects.
Even if they were not geometric objects. So what is special about, do you have a feeling for what is special about these orbifolds? Is there something you expected that these guys were special? What lesson should I take away from this?
I basically had to do my PhD, but when see, I am not, well, I don't know. But for this Moonshinein, it's interesting also, like you can, you were writing the twisted elliptic genus in terms of super conformal characters, and these things were totally unrelated. I mean, how would you? I mean, it's okay. You can write in terms of super conformal characters, but why should these numbers at all have any relation to the any relation to the characters of M24, or why should that happen? I mean, that itself is a very weird thing for me. I myself don't know why somebody would even look at that.
And the fact that something good happens for these particular monster orbifolds sounds very interesting.
Yeah, but
I mean, it sounds like this monster thing has something
physical, yeah.
So it would be nice to have a story, even if it's not completely correct. Some story that, some words that make you understand why this is.
Okay, no, but we don't exactly have that kind of an understanding.
Okay.
At least I don't.
Okay, no, it sounds very interesting.